I have two. Ah! This is weird. Okay, now I had sound for a little bit. Okay. Okay.
You can keep it with the others. If they tell something, I can listen. Open your mic.
Yeah, sure.
Okay, now I have sound again.
Hello.
Check with Jackie if he's listening.
I can mute my sound.
Professor Borges, please check if he is able to listen to you.
So I just heard Reinhard speaking now.
Can you open your microphone, please? Good. Jackie, can you hear us now?
Yeah, now I can hear you very well.
Where's the other assistant? But we cannot hear you, Jackie.
I can hear you well. Okay, then never mind. Then you guys go ahead and I try and
Jackie,
sort out
we
my
cannot hear
problems.
you.
Go ahead and I will
Up there near you,
fix my problem.
we have the video conference system there. I can hear you, but you cannot.
Okay, testing, testing, testing. Okay, 5 minutes, good. Then let me see if I can try and reconnect. Oh, I'm muted now by the server. Can you hear me now? And we have not, okay, okay. And then, okay, can you hear me now? Okay, good. Phew. Okay, good. Okay, now.
Okay, die liegen also einfach los. And you should share your screen here also. Okay, you can start if you like.
Okay.
When you should share your screen.
How am I going to show? I'm not going to show.
Where are they now?
And then you need to select if you want to share the window, the application, or the entire screen.
Non, ce serait difficile. Je ne vois pas
I would like to share the entire screen.
Looks like Jackie sharing the screen now. Or some other Chinese, Taiwanese.
And there is also fire application.
Okay, I see the slides now.
Now it's Jackie sharing the screen.
Il voyait déjà. Et puis c'est projeté voilà, au-dessus de la télé. Il voyait déjà. On n'a pas besoin de faire ça.
Okay.
Just make your volume
One action.
here. It is here.
It's here, right? Okay.
Non, c'est pas. Il faut rester là. Je dis non, il va passer.
Okay, I think we are ready now. Sorry for the delay. We may have to work on a more stable infrastructure, but that's an issue for the summer break, not for now. So please go ahead.
Okay, thank you. Hello everyone. Today we are going to present our exercise on a start uses a heuristic to bias the search in the expected direction of the goal. Why can it only use a heuristic, not the actual lens? Let's go over the structure of our presentations. Okay. First, we will present the HTAG algorithm and the actual length. On next, a short case study on the, and finally, our implementation. The HTAG algorithm and the actual length. The HTAG search algorithm is a pathfinding algorithm that finds the single path shortest path between the start node and the target node of a weather graph. Here you can see the formula that we use in our exercise. F of n is the estimate of the total cost from start node to target node to node n. And J of n is the actual cost from start node to node n. Here you can see our heuristic function, the estimate cost from node n to target node. Then why we use a heuristic instead the actual length? Practically, it is used to calculate the actual length for every possible node requires prior knowledge of the optimal path which defeats purpose of the search. Efficiency, it is used to help guide the search process efficiently towards the goal without having to explore every possible path. On scalability, in large or complex grid, computing actual length for all nodes is computationally expensive and often impractical. Now, our case study.
Yeah. Let us move to our case study. Here we take an example for a 10 by 10 grid where each cell represented a navigable space and the possible moves are to go up, down, right on with a cost of 1 for each move. And in our case study, we are going to explain the difference between the length actual and the heuristic. Here it is the presentation of our grid. It is the grid of 10 by 10. We consider here that we have our destination here and we want to move from any node here so as to reach the destination. Yeah, here it is how we find the actual length, which is the actual cost, and the actual length is the real cost to go from the node to the goal G. And here we have our example. We have agreed our what we see before of 10 by 10, and we want to move, for example, at the node, at the position 2, 2, so as to reach this place. The actual length with, for example, the JISCA algorithm we use will go down 7 times and 7 times right, so to find the destination. And first of all, he will map all this space so as to find the right course. But heuristic is not function doesn't function like that. First of all, heuristic will base will use Manhattan distance maybe for the grid so as to calculate the right course between these 2 points. Let us move forward so as to see how this can be calculated. And for example, we have our starting point here. I will take another one, for example, here, and we want to reach this point. First of all, we will calculate this distance with heuristic, which is the difference between the x-axis from the from the end point to the between the end point and the starting point, and the y-axis out also. And we will take also its neighbor for the starting point node, and the neighbor also for the target node. And based on this, the heuristic algorithm will use this so as to get a search toward the destination without mapping first of all And here is further explanation for the calculation of the labor and so on. Here, let us move to the implementation part. And here is our comparison. It means that we don't know if we know the cost in advance, we cannot use any more heuristic so as to provide our the length between these 2 points. And here it is an application. Okay. Yeah, here is our grid. And for example, I will first of all set my destination here. Here, for example, and I will put also my starting point so as to see how this algorithm here is as A star, and here is our discount algorithm. For example, here. We see here the R algorithm has already defined the destination, and the discount algorithm is still mapping. And yes, it is also the same cost, but here it is faster than the second one. We will do also the next step with some obstacles so as to see how it's working.
Share the screen in the video conferences. Please.
Here. And here you can share your screen. And where's the system? Here, right? Okay, good.
Okay. The second example is with some obstacle here, and we generate the map with some obstacle and set our destination. For example, here, and our starting point here, for example. Yeah, both of them have already defined the destination, and we can see that this algorithm use heuristic so as to guide the search toward the goal when this will first of all map and then find the right port between these two nodes. That is the end of our presentation. Thank you for your kind attention, and we are open to questions.
Thank you. Yeah. Maybe first question, this nice application to play with, where did you find it? Maybe you can share, or did you do it yourself?
Yeah, we contribute to it, but it is the code. It is on my computer.
Would you be willing to share this with your fellow students so they can also try?
Yeah, I can put it on.
Wiki, file, whatever.
Okay.
I think that would be very helpful. Okay, so any further questions?
So I have a question. When you discussed your A-star algorithm, you talked about the movements that the robot could do. which is up, you
Yeah.
said up, down, left, and right. And then for your heuristic function, you use the Manhattan distance, which is the difference in rows plus the difference in columns. So it would be following a grid cell. But when I look at your output now, at your program there, then it seems like the robot can move diagonally as well, right? Like the robot
Yeah.
goes
It
diagonally
is just because.
to the bottom left. So now what happens if you do not change your heuristic? What will actually happen now?
I don't get really the question.
Like you said, your robot can only move up, down, left, and right, which is 4 directions, right? But
Yeah.
what you draw, you can move in 8 directions. You can move diagonally.
Okay. Here we cannot move directly because we have a grid.
No,
We have a
but
grid here.
at the green one is a start, right?
Yeah.
Okay. If the green one is the start, then what's the first move that you make? In your solution, the yellow path is the solution, right?
Yeah.
Yeah. So the first move seems to me to be go down and to the left, correct?
Yeah.
And then another go down and to the left. But that's not one of the 4 moves that you said your algorithm can do.
Yeah, it is what I said because in what we implemented, we were supposed to mark this cell so as to show that it go down before turning right. But considering that we are using our turtle boat, we didn't take it into account because we just represent our grid so that our robot can move. It can use any direction so as to move. Yeah,
Okay, sure, you can do
it can
that.
follow.
You can make your robot move diagonally. My question is, if you change, let me just type the question so that you can understand it better. Maybe if you change the mobility of your robot
He's typing, probably lost the audio.
to also to 8 directions.
Well, the question is, you had a heuristic,
Yeah,
which
Then what
assumes
happens to
4
your
directions to move,
heuristic?
yeah.
but you use 8 direction. Actually, you used 8 direction for the robots to move. So the heuristics and the movement don't match.
I say that we use a grid. I was supposed to put in my application, for example, that the robot move from here to here and from here to here. But I didn't set
Okay.
it to this case
Yeah.
in my application. I did.
So-
I directly showed you.
Apparently,
Yeah, I can
going
move
from
down.
here to there is 2
move-
steps.
Yeah.
So the cost would be 2 and not 1.
Yeah.
That
That
is
is
2
what I
steps.
show here.
Okay, so let's say you make it 1 step. Then what happens? Okay.
Que c'est un problème. Là.
Ele pune que só consegue só me conecta com isso com a isso.
Non, comment là?
Or maybe I
Uh,
should
by the way, any questions on your side? So if we have something like this in the exam or later in your professional work, would you be able to deal with it?
Comment on a compris ce que comment ça fait?
Does the Manhattan distance describe the diagonal path to the target node?
Please?
You talked about using the Manhattan distance as an heuristic.
Yeah.
And if I remember correctly, the Manhattan distance always describes or denotes the diagonal path from the target, from the start node to the target node, correct?
Yeah.
Okay. So the heuristic basically allows traveling diagonally.
a heuristic
Because the
doesn't.
Manhattan distance always is the shortest path, and thereby using the diagonal path in a grid. So
Not necessarily.
how's the Manhattan distance related to the moves the robot can do?
Well, it's a heuristic.
Yeah.
So, it could be any kind of measure which not necessarily relates to the real costs afterward.
Sure. But when using the Manhattan distance, I got the diagonally shortest path.
No, Manhattan is X, Y directions.
What?
Ah,
Yeah.
yeah, but
Okay, so let me ask them, what is an admissible heuristic?
That was a question for you.
My question?
No, what's an admissible heuristic for your function h of n?
Yeah.
What kind of function you can use for that in your case? So you've chosen the Manhattan distance
Yeah.
as your heuristics.
Yeah.
Could there be any other heuristics, any other estimation?
I think that in robotics we can also use the Euclidean distance.
Okay, Euclidean distance.
Yeah.
Does everyone know what the Euclidean distance is?
The Euclidean distance is we calculate between that is always between 2 points. I can put the formula here.
Yeah. Well, how does Manhattan distance and Euclidean distance relate to each other? How do they relate to each other?
I think that we have our 2 points.
Oh, that's complicated. Do you understand?
it's basically the length of the vector.
Okay, you can remove from this. Great.
Remove all but what is
This is our Euclidean distance. How to calculate?
Okay. Could you sketch it on your grid?
Here we have our y. We have y and x axis.
Okay.
Here, for example, we want to. That is our, for example, b at the position 0, 0. And here at the position we have a grid 10 by 10, and B is our at the position 9.
Now just draw a line to represent the Euclidean distance between A and B. Perfect. Okay, and the blue one,
Yeah.
would be the Manhattan distance.
Yeah.
Okay, so what's an admissible heuristic then? Which heuristic would give you, what makes, there's also an algorithm called A star is a special kind of algorithm which has an admissible heuristic. If you consider your robot can only drive up, down, left, and right, then which one would be the better heuristic? Which one would you choose? Manhattan distance or Euclidean distance?
Okay. I think that we will choose the Euclidean distance.
You would choose for which kind of robot? Four directions or 8-direction robot?
4 direction.
For 4-direction, you would use the Euclidean distance. And why do you think that is better?
Yeah, I think that because it is the shortest path that the robot can follow.
Okay, I couldn't quite catch that, why you mentioned. Can you repeat it, what you just said? Or speak louder?
Yeah, I say that I choose this because it is the shortest path that the robot can follow.
Right. Okay. So the crucial component of the A star algorithm is a heuristic function that is admissible. Admissible means that anybody else know?
Never overestimates the path to the, or the true cost to the target.
Correct. It must be an underestimate of the true cost to the goal. So if you have a robot that can move in 8 directions and you choose the Manhattan distance, then what will happen? Or actually, if you have a robot that can move in 8 directions, then the Euclidean distance is guaranteed to be an underestimate, because to go from 0, 0 to 9, 9, it'll take you the square root of 10 plus 10 squared plus 10 squared, give you the square root of 10 steps, right?
Yeah.
If you choose the Manhattan distance, then it will tell you from 0 to 9 is 10, and from along the columns and 10 along the rows, and it'll give you a distance of 20, which is not an underestimate anymore, right? Because you can, if your robot can move in 8 directions, you can do it in 10 moves instead of 20. So,
Yeah.
in that case, your heuristic is not admissible anymore. So what happens to the A star algorithm if you use a non-admissible heuristic? If you use a heuristic that may sometimes give you an overestimate of the distance to the goal.
It would revert back to the Dijkstra algorithm, at least in some parts of the map where the heuristic isn't optimal.
Correct. It won't deter, usually it doesn't degrade to the Dijkstra algorithm, but the crucial fact about the A-star algorithm and an admissible heuristic is that as long as your heuristic is admissible, you're guaranteed to find the optimal path, the shortest path. If your heuristic is not admissible, then you will find a path that may or may not be optimal. It may or may not be the shortest path. So that's why if I look at the visualization and you use Manhattan distance for the robot on the left-hand side that can move diagonally, then you may get a solution that is not optimal. So for a robot that can move only 4 directions, then the Manhattan distance actually is correct as far as it is admissible. The Manhattan distance would be an admissible heuristic for a robot that can move in 4 directions, but not one for a robot that can move in 8 directions. So this is one of the fundamental concepts in A-star search. That's why we always try and find an underestimate for our heuristics. And that's why changing from a robot that can move in 4 directions to one that can move in 8 directions must be carefully considered. You need to also adjust your heuristic function.
Okay, all right.
Now, what would be a good heuristics for a robot that could go any angle? Not just 8 directions, but let's say 360 directions.
Any direction?
Any direction. Yeah.
Yeah, I think that it is Manhattan. To use Manhattan first.
You would say it's Manhattan
Yeah.
for a robot that can go any direction. Any opinions on that?
A robot that can turn in any direction will basically take the diagonal lines. So the without any obstacles, the Euclidean distance would be the right path, the shortest path, basically.
So,
But then we have the problem that it's not underestimating; it's basically estimating the exact.
would that be okay? Would that be admissible?
I think the definition of admissible is that it underestimates the true cost. And by using the Euclidean distance, this is not guaranteed.
It needs to underestimate. Is this a true less than or less or equal? Could someone please check with some resources? What else could we do with the robot?
No,
that
I
can
mean
go-
less than equal is okay for the heuristic, isn't it? Yeah, sure.
Okay, 2 options.
Never overestimate. Yeah.
Either you check the internet or you ask Professor Baldwin. Huh?
Oh, sorry,
No problem.
I wasn't.
All right.
No, it's fine. Okay.
Okay.
Well, one more hint. Sometimes you see these examples not with a grid, but with a graph. So maybe you want to check out how the A stuff with the graph representation. Let's say going from here to Taiwan via Tehran, Delhi, and well, Beijing or something like that. And then there may be you can also take the path via Moscow. So what kind of heuristics you can use for that? Let's assume you want to take an airplane. Just think about it, huh? Okay. Any further questions on for our experts? No. Okay. So who's next? Yeah, thank you.
You're welcome.
Ah, there's the speaker and the projector. Oh, somebody else. Well, please mute your microphone. Well, because they still have.
So, Jackie, can you hear me?
Yeah.
Good. So I will share my screen now. First, we'll start the presentation. So, let me share my screen.
Let's focus on this one because it may be an issue with the Excel. And for example, with the well, I think you can use all the microphones.
Yeah, thank you.
Okay. With respect to the Excel, you may want to consider to use this for the NFL, huh? Because you need to find, well, you're running against the clock, huh? So you should find the short.
Okay, 2 weeks ago, Jackie, can you hear us, right?
Yeah, I can hear you.
muted
Thank you.
But I think yes. Okay, it's because he's muted. We have some feedback, but
Oh.
yes, I think he will. There.
Sorry, I can hear you very well, Matteo. Sorry, I didn't realize
Good.
I was muted.
Okay, can you mute? Because we have some feedback from you also, so it's just...
Can I do what?
Can you mute your microphone? So,
Yeah.
because...
Yeah.
Good. You? So 2 weeks ago, we made a presentation related about feature structure chapter. And we present about the chapter feature extraction. So, and we talked about the huge transform. And with this, I come back to explain more concepts about this kind of techniques. And also, I will explain about the concepts, and Libby will show us some examples and some pictures how step-by-step works. So just one review. 2 weeks ago, we talked about these three different environments for feature extraction. We talked about each feature we could use as information for these three different ones. Here also we have Whitehouse, and the last one we have a cave. That these three different scenarios and environments, we have three different characteristics or parameters or features that we can work on. But for today, we want to talk about the feature extraction and also huge transform. So what other features, the question should be that we want to answer for you, it's what other features could you detect using huge transform, and can you find parameterizations for cycle, square, or triangle? So these two questions, and after this presentation, we can talk better about if you understood or not, and we can try to check about it. So the first thing, some concepts about the huge transform. Huge transform is a powerful feature extraction technique that uses to image analysis, computer vision, or image process, and we can use some edges for the picture to identify some shapes and line shapes or different shapes to extract information. So let's start using the simple concept. The first here we have the image space with a lot of, we have a bunch of edges, as we can see here on this image we use here. And we would like to identify the line here, the straight line on this image. So how we should do it, how we can understand to identify this kind of line. All of us know that the straight line can be described for this function. Y is equal mx plus c. So this is a simple equation, a simple function that can describe a line. But also this line can be described based in the parameter space. When we use y is equal mx plus c, we have image space. But also here we have the parameter space that we use the parameters like c equal minus mx plus y. That x and y is unknown. So both functions here describe the same. The first one is in image space. The second one is in parameter space. So what it means for the parameter space? Here we describe the values for C and M. So all the values for C and M that describe lines that pass through some specific point here and X and Y. So for example, this point here, we have all of these values for C and M, the combination for values for C and M for this function that describe all of the lines that cross this point here. So when we take all of the points for this line, all of the edges for this line, we have also all of the values for C and Y that describe for each point. What is important here for us? That we can identify the intersection between this parameter space. And when we have the intersection, we have the value for the M and C that describe exactly here this line in orange. In case, for example, we have an edge outside for this line here, for example, this green one here, we have also the values for C and M that describe for this all of the lines that cross this point here. But as we can see, this green here, there's no interception point, as we can see here in MC. So we can take the parameters, the MC values that describe this line here. So in resume, we have point in image space is can represent a line for the parameter space, and the parameter space of one point it's equal one line for image space. Okay, so based in this concept that we understood, how one basic line that can work. So the first thing we have here one image, a simple image with three edges, and the first thing we should create one array, one accumulator array that we have here the parameter space. So we have C, we have M, and the first thing for this image we should create the parameter space array that we can decide about the accumulator. The next step, we should set 0 for all cells for this array here. So as we can see. And the step 4, what should we do? For each edge, we should fill as 1 for the values for each edge, we should add 1 for each cell for the line. So as we remember for the parameter C, for the parameter space, we have one line there. For each value for M and C, we have all the lines that cross the image space. We will do the same thing here, but using an array. So for example, the first edge, we have these here, these values here, that for each cell. For the second one, we have now these cells here is the values for C and M for the specific edge. And the last one, for example, we have these 3 here. And as we can see, we can find the interception point. It's like, Jackie, if I'm wrong, please, you can talk about it later, but this here, it's equal a voting for the rouge. So we have here the values for each edge, and after that, we should identify the local maxima in this array here. And these 3 here that we have the voting, we have value for C and M that describe this red line here, where we have a maximum for this, okay? So this is a simple concept for the line detection algorithm. And for multiple line detection, we should follow the same concept. So here we have the edge for the image, for example, in the image space. And for each point, each edge that we have here, we can represent in the parameter space. And for these 4 kinds of combinations here that we have the values for C and M, and also the interception point here should be the C and M for each line that we have in this image space. Okay, so we have 4 different lines. We have this representation here for the parameter space. But what is the problem that we use the parameter space using M and C? The issue here is because when we have this kind of representation, we have infinite possibilities, values for M. So this requires a large accumulator and also more memory and computation that when we create a script based on this concept. So what should be the solution? One possible solution is we use this representation here based in the angulation that the line or arrow that we have with the horizontal coordinate in case X, and also we have we can consider O, that is the distance from the line to the origin. So these two parameters that we are using are finite because we have angulation that we have. I think the values that we can have, it's 0 to pi. And also we have rho, it's a distance, so it can be finite. It's something that we can measure. So how we can do it? We have this equation here in the image space that we have x and y. And when we change for parameter space, now we are looking for theta and rho. And for each point for the image space, we have one sinusoid here. This wave or sinusoid that we can see the signal here. So for each one, for example, this point here, this point or this edge here on the image, we have the representation here, and the second one we also have the representation, and for all of the edge for the line we have one sinusoid that can represent the values for rho and theta for this kind of image here, okay, image space. And when we have all of them, we have the same concept that we use for the line, that the intersection point can represent the values for each one, the line. Okay? So here it's more visual that we can understand this kind of concept. We have one script that can come for line by line for the frame, and here, for each value for the edge that we find it, we analyze the rho and theta. And we can create a graphical representation here for values for rho and theta. And if we wait a little bit more, we can see where we have an intersection point that we can see where is the line is. So it's like a representation. If we wait a little bit, but if we look here, we have 1, 2, 3, and the last one will appear when we start looking for these edges here. So let's wait for, yes, it's coming here. And as we can see here, the red, for example, represents this line here. And for these 4 can describe these other 4 lines, and we can combine them to identify the shape on the image space. So this is using for shapes like lines, triangles, rectangles, or squares. And here, we can also, I will start a different shape, like a circle, but using the same concept. We have, for example, the formula or the function that described in the circle in the image space here, and we can move for the parameter space. That now it's not related about the x and y, but it's more related about a and b that are the parameters. So for each edge or point for this circle here, for that describe this circle, we have one equivalent circle for parameters space. And if we do for all of the edge for this circle here, we have all of the parameter space representation. And again, we look for intersection point here, that it's exactly the values for B and A that will describe this circle here. So we can take all of the edge and we make the combination, and here we have the values for A and B that we can describe the circle in the image space. Now Livin will show us more visual things and how we can do it by code.
Okay, thank you, Matthias. And after we learning about the theory, now we start to program by ourselves and search some example of transformation. And firstly, we did this kind of circle detection use concept that Matthias explained before. We just firstly use the edge detection using the Sobel filter, and then use the whole circle from the CV2 package to detect the circle. And as you can see here, the white line already like label the things that we want. And next, we found we found a few examples about rectangle detection. And first, we are trying to detect some rectangle in black and white picture, and we don't need to do the edge detection anymore because it's already like. And then we can see this corresponding Hof painters, which is exactly that Matthias explained before. As we can see, every possible line are like described here or represented here as the curve with sine function. And here, the intersection of these 4 points are the 4 lines of the rectangle. And this algorithm are trying to like firstly turn this rectangle picture to this corresponding whole painters, and then according to the point of the corresponding whole painters, and to transform it into the detected rectangle. And after that, we found another example of the rectangle detection. It's a little bit different. He firstly used the image preparation, like use grayscale and applying blurring and detects the age, use the Canny method, and then he used the Hof transformation. And we already know that rectangle cannot directly detected by the Hof transformation, but add more condition like clustering and filtering and like corner detection. And after that, we can like filter the rectangle to find the real one or the standard one. And after we read the example, we tried it by ourselves. This is more examples that we did. We firstly use like the age detection to like to make the age more obviously, and then use the Hof transformation to detect the line. And then we filter the line with like a parallel condition and the perpendicular condition to find the rectangle. And at the end, we can see here this red lines already like detect this square, but we also have some problem. We can't delete this line. I think maybe it's because we didn't consider about the intersection between two lines should be on the line. That's why this line is still here. So for the conclusion, we would say, for the line and the circle, we are able to detect it with like according to the geometric features, but for the triangle and the rectangle and square or something like that, we can use line detection with Hof transformation, but we need to like add more condition function to do that, to detect the real rectangle and triangle. And this was about what we want to say. Thanks.
Okay. Any?
One thing is if you go back to your slide for the lines, your angle theta is wrong. There, that's
This
not
here?
theta. Theta is the angle of the origin to point P, that angle with the x-axis. So theta should be 90 degrees.
Minus this theta. Yes,
It's not to the y, it's from there to x. If you go to the P and then draw a circle to the right until you hit x, so rho should be, not P, rho should be about 135 degrees or something like that. in that
Sorry,
image
Jackie,
that you
I
have on
didn't.
the left-hand
This
side.
here, right? This one.
This one here. Okay,
Yeah,
this
yeah,
here.
yeah.
Yeah.
Okay, so the angulation. Okay,
Yeah.
sorry.
And
me too.
more importantly, how would you, if you want to find rectangles using a half-spaced approach, then how many dimensions would you have in your half space?
To detect the rectangle,
2, and which 2?
I think it's exactly here, the theta and the rho.
That's if you're looking for lines, right? If you're looking for rectangles,
Because I detect the rectangle using line detection, and then I add more like some parallel and
right?
perpendicular.
But if you were to use a half space approach, then you would define a rectangle as a shape that has 4 parameters. It has the x location, the y location, the width, and the height of the rectangle. That gives you a 4-dimensional space then, and that would be your accumulator space. Using a generalized half transform, you're not limited to 2 dimensions. You can have as many dimensions as you want.
Yeah.
So you would not detect the 2 lines, parallel lines first, and then try and build a rectangle out of that. You can of course implement that, but it wouldn't be a generalized half transform. It would be some kind of hybrid approach.
Yeah, makes sense.
Now, what would be the disadvantage of finding rectangles using a generalized half transform? Why would your method actually possibly work better?
Well, anyone could help, huh? Could
Yeah.
provide an.
He asked why humans both informations.
Because it reduces the complexity by adding the context of the rectangle as additional information provided by the programmer and not provided by the algorithm.
Yeah, that's correct. So adding too many dimensions greatly increases the size, the memory requirement for your half space, right? Because if you have 2, then it's squared. If you have 3, you have cubed. If it's to the power of 4, then it's already pretty big. And let me just draw something here quickly. Can you see my whiteboard here? If this is your image,
Yes.
Not yet, Jackie.
let me draw that.
Is there?
Yeah, okay, now, yeah.
It's not possible.
It's
He's sharing his screen.
Well, I can also draw it in the notepad actually. Wasn't there?
It would be better.
yeah, you take presenter and then move 1 slide ahead. There should be a white slide to draw on.
I take the paper. Okay.
No, presenter. The plus sign at the bottom.
Okay, plus sign at the bottom. Presenter, okay. Okay, now I have big blue button and then one to the right. Okay, good, yes. So if my image looks like this, after edge detection, this is the output of my edge detection algorithm. This is the image. What line will be returned by the Huff line algorithm? What will be the output of your Huff line algorithm?
I think there will be like every line here we drew will be detected as
The
lines
maximum, we
and
find the strongest line using a Huff space algorithm, a Huff line algorithm. We find the strongest line, right? So which one will be the strongest line?
Yes.
how to say that?
Which one?
This here, that takes all
I
of
cannot see your screen. I can only see this one.
Jackie, should be a line that is perpendicular for all of these that you draw in vertical.
Yeah, there will be a line that goes through all of this line.
Correct, yes.
Detected, I think.
And it would look something like that, right? Because the Huff line algorithm, the standard implementation, will only try and fix all the points, make them one line, whereas what you would expect would be this line, right? You would expect it to return this line here. That would be the longest line that you actually have in your image. But the Huff space doesn't care about connectivity and also the gradient. Now there are ways to fix that by taking the gradient information of your edges into consideration. In that case, you could say that a pixel that has a horizontal gradient shouldn't be allowed to vote for vertical lines, that kind of thing, for example. And the same thing can happen if you're trying to figure rectangles. You may also get into trouble with that, and the problem of that happening greatly increases as you increase the number of dimensions. So that's why I would not recommend using any parameterized shape with 4 dimensions or more. Even though that is possible, chances are that there's, due to the curse of dimensionality, chances are you will get some other shapes found by your algorithm which are not actually supported by your image. But in theory, you can find rectangles by just looking for x and y and width and height, because those would be the parameters for your rectangle. Okay, that's all I have.
Thank you.
Well, maybe just one more collective question for everyone to contribute. So what would be the approach to detect a triangle then? How would you do this? From the audience. What's a special property of triangle?
Sum of the inside angles is 1/8.
I think it's corner.
The sum of the angles 180 degrees. Okay. Now we heard this ideas about detecting squares. So how could this be done? And about the dimensions, about the complexity. Be your approach.
I think detecting the corner will be better to do.
Detecting the corners.
Yeah. But then it's not off transformation.
Should detect the lines first, check the intersection.
So you wanted to detect a square by detecting lines and then see
then
the lines are parallel.
I filter it with parallel condition and a perpendicular condition and delete some lines that have very close distance.
So that would be a kind of hybrid approach. So how would you do this with triangles then?
For triangle, I would say I will first detect 3 lines which has intersection and confirm the angle of the triangle, I think. But it's very hard, I think.
So could be an option, but we're not sure. So maybe we would like to be sure about this. So let's do a small exercise to check what literature says about detecting triangles.
Okay.
Around a half or hybrid approach. Okay, any further questions from our experts? No? Anyone else for presentation today? Let's go.
Good. So let me close my.
Okay, good. So is there another presentation? Ah, yes.
Now?
Yeah.
Third step is calculating motor speed. Is based on the sensor values. The robot calculates motor speed to flow the line. If the center's sensor detect the line, the robot goes straight. If the left or right sensor detect the line, the robot adjusts its path. Next step is adjusting speeds. Motor speed is adjusted to stay within safe operational limits, ensuring smooth and reliable performance. In next step is applying speeds. The adjusted speed are applied to the motors, directing the robots to flow the line correctly. Uh, uh, Last step is a continuous loop. The system runs continuously reading sensor and adjusting motor speed in real time, ensuring the robot dynamically follow the line.
Thank you. Yeah, the exercise is about Breitenberg formalism. We learned in chapter 11 that the Breitenberg vehicles are simple robots that can do complex behavior based on simple sensor readings. In the book Vehicles from the Breitenberg, we have two sample, very simple vehicles. The first one is they have just one sensor and one motor, and if the sensor senses, for example, the light, it can drive the motor and just go in a straight line. Vehicle 2, that is in the book Vehicles from the Breitenberg, we have two sensors connected to two motors. and we have two configurations. One of them is the parallel, and one of them is the opposite configurations. And if we remember, for example, this parallel, what does this parallel do? This parallel moves away from the light source. We have two light sensors. If the right sensor senses more, then the speed of the right wheel will increase and turns this way. And the vehicle 2, if we connect just these two sensors in the opposite wheels, it can follow the light source. The concept is just use sensors to drive wheels. In this example, we have this robot. The robot has two wheels and three sensors. One sensor on the left side, one sensor on the middle, in the center, and one sensor on the right. And each one of these black points are our sensors, and they read these orange points on the ground. And on the ground, we have just two colors, a black line in a white environment. And how we decided to control this robot? If it reads the white, for example, it returns the 255 in our simulation, and if it reads the black, it returns 0. And now how we decide to control our robot? We use a simple if and else conditions. If the sensor at the start, the error is 0, and we start driving straight. And if the sensor on the center detects a value 0, it's less than 128, the error remains 0. If the left senses, the error is -1. And if the right senses, the error is 1. And then we could just adjust the right speed, right wheel speed, and the left wheel speed with these errors. And what's the correction? The correction is an alpha multiplied by an error. And alpha, we define it to adjust the turning speed for different velocities of the robot. And it's a demonstration of our robot. Robot starts to go straight, and then just the middle sensor senses. And if it goes more straight, the middle sensor and the right sensor senses white, and just the left sensor senses the black. The robot turns and follows the path. So we just use the simple solution. The other solutions were available, but yeah, the Breitenberg is about the simplicity, and we used the simple one. Now Alireza should.
Thank you. We simulated a line following robot using Python to show you how the robot follows the black line on a white background. As explained, the robot has 3 sensors, left, right, and center, to detect the black line and adjust the wheel speed. Okay, I will run the simulation.
Just a moment, please. Did we lose the presentation? Did we lose the presentation? We're sharing the screen.
No, it's there.
Okay.
Okay, it's an. Okay, it's our code for this simulation. So I will run it. So we have a black path, black line, and the red circle is our robot. These three small circles are our sensors. Okay. Okay. We took some screenshots from the terminal after running the simulation to show you what happened on the background. So in our simulation, as you saw, we had 4 turns, 2 left turning and 2 right. Okay. As you can see, we have the sensor readings and the wheel speeds. At the beginning of simulation, the center sensor detects the black line and the speed of wheels. Both of them are 2. So the robot moves straight. And so after that, as you see, the robot reaches a left turn. This means the left sensor detects the black line. So and the robot adjusts its speed, the speed of wheel. So the robot can follow the black line. Okay, and then as you can see, the robot again moves straightly. So the sensor, the center sensor show 0. That means the sensor detect the black line again. And okay, thank you for your attention.
Okay. First comment, if you want to share code on a video conference, you may consider increasing the font size. You may not be able to fit all your code on one page, but this typically is one of the issues. Okay, aside of that, any questions? And well, this is not only for you, this is for everyone.
No.
So I have a question. So you use 3 light sensors at the moment. Could you have done it with 2?
Yeah, we could have done it with 2.
So can you change your
the
code?
question was, yeah, just a moment. Now, no, we don't see the code.
Like if you show me the if.
Yeah, I'm gonna. Yeah, this is the code, and now this is the part that I showed in the presentation. And the question was to do it with 3, and in another code we have done it with 2. Yeah, for example, if we just calculate the error from the left sensor minus the right sensor, it should work too. I'm gonna run it again.
Center sensor is deactivated.
No, but that's 3.
That's 3.
It's 3, but for the error calculation, we just use the left and the right sensor in this simulation.
Okay, but that's not really error, I would say, but okay. Yeah, very nice. And if you swap the background, so instead of black line on white, you have a white line on black, then what changes would you have to make?
I haven't tried it, but
We haven't.
can try.
Just a moment.
The color.
No, no. اگه چه تغییری باید انجام بدیم I haven't maybe just a moment.
The pass. Draw the pass. Draw the line.
No, just the in begin black, in begin
White.
white.
Mm-hmm. Yeah,
What are the
exactly.
changes? Just
Which I guess is one example of. It's one example of. Yeah. Okay.
I just changed this the error from the left minus right to right minus left, and
So thank you very much. That was very nicely done, and it basically shows what's quite surprising about the simple Breitenberg controller is that you can get a wide range of behaviors and support different environments with these very simple rules without actually making many changes. Which is what makes that particular approach, this kind of reactive controller approach, quite impressive. So with a set of very simple rules, you can generate some very complex behaviors for a variety of different environments. So thanks a lot. That was very nicely done.
thank you. Thank you.
Yeah, now there's a question for the entire course. Could we, maybe first mentioning, these are analog sensors you've been using, but you have been using them in a Boolean way. So it's either 0 or 255. Let's assume we have an entire range, kind of a grayscale sensor with some integrative properties. Could you do the line following with just a single sensor? This is
Single,
not only for you.
But the single sensor that just detect a point, or
That outputs a range between 0 and 255, depending on what it sees.
and how's the path? The path is just black, or the path is that gray too?
Well, no. The path is either white on black background or black on white background.
Where should it be placed?
At the center.
Wherever you like. Would work, okay.
Because you can't detect in which direction the robot deviates from the path. If the path is the same color through and through, the deviation to the right side should look the same as the deviation to the left side. If I only have a photoresistor that measures reflection of the ground.
Okay, let's turn this into a global exercise for the entire course, and we will see a question. The answer is yes, it can be done. There are some assumptions. We indicated one of these. It's an analog sensor which outputs the range between 0 and 255. And there's some other properties. Okay, yeah, good. So you may want to have a meeting in the And hopefully we'll see all correct answers to this. I think those guys who.
Yeah.
Okay, another question. Had a simulation. I really love that. But it's overly realistic, huh? Because you always had a clear 0 to 255. So typically there's some stray light, bad reflection, some dirt or stuff like that. So how could you model this kind of issues in your simulation?
In the real world, even in the real world.
You could simulate some of the issues you have in the real world in your simulation.
One of the things that we considered is the last known direction in the code. And it helped, for example, let me run it again. For example, here, it's still turning left because it's the last known direction. But all the three sensors are returning the white. No, this last known direction was a good thing to help, because once we know that we have to turn left, we turn until we know that we're on the path.
Which initially is part of the Breitenberg approach, huh?
Yeah.
That's purely reactive, and you have a kind of a memory. Now, real-world issues typically relate to sensor problems. So you would have to, in your simulation, you would have to change the way you provide the sensor values, you calculate the sensor values. And maybe to cut this short, one of the crucial issues is sensor noise. And sensor noise would be random value to add to the, or to subtract from the sensor values. So if you could change randomly from 255 to, let's say, 250, something like that. Of course, you will not have more than 255 with an 8-bit sensor. This could turn into a more realistic setting, and it may indicate some issues which may occur in reality, but you wouldn't see in the simulation.
This kind of simulation.
Okay. Any further questions? Yeah. So thank you. I think we have one more presentation. No, more questions.
More presentations.
More
not
presentation.
questions.
Yeah. We have more presentations.
It's the last week, I think.
Yes, last opportunity. It's now or never.
Now, never.
Okay, good. Yeah. Whoever wants to be next. Yeah, you just go off to the lawn and find
نبود من نوتام همه پاک بود آخرین ورژن نبود نه اضافه کرده بودم
چرا بابا دانلود کرده بودم
ولی توی چیز منم نبود اون صفحه لود نداشت بیا پای بفرست
همین الان اینو دانلود کرده بودم.
اشکال نداره هندلش کردم
آره ولی همین که جکی راضیه میگه
Du musst auf den Bildschirm fahren.
Ah, ja.
Jetzt gehen wir nochmal zurück. Du hast noch nicht dein Bildschirm geteilt. Also. Jetzt entweder Fenster oder ganzen Bildschirm. Und dann kannst du
What is presentation? No.
Nee, mach.
Oh, yeah. Yes.
Du kannst es einfach nach Windows und dann. Genau. Oder da. Den musst du, glaube ich, nehmen. Geht nicht? Wie steht der jetzt? Sieht gut aus.
Yeah.
Ja, schön zu passen.
Go.
Ja.
Yeah.
Hello everyone. We are Junior, Marcus, and Roman. We are there to talk about propagation of full sentences. We will start by explaining the exercise. Then we will give some examples from the real world. After that, we'll present the theoretical basis needed to solve the exercise. And finally, we will present our solution. Our task will be to solve the following exercise. Consider a unicycle that turns with angular velocity v and has radius r. Its speed is thus a function of v and r and is given by v equals rv. Assume that your measurement of phi is noisy and has standard deviation sigma. Use the error propagation law to calculate the resulting variance of your speed estimate sigma squared. The error propagation is essential to ensure the accuracy and reliability of measurement and calculation of various fields. For example, in robotics, when measurement position of temperature sensor. It is also used in physics when measuring various physical quantities, such as speed, acceleration, temperature, pressure. Marcus will show how the basic concept used to solve the
yeah, so all the shown real-world examples on the slide before, so basically the Segway or even the unicycle, which is not robot-related but describes the problem, boil down to a concept known from especially physics as an inverted pendulum. Basically, we have a mass up there attached by a stick to a moving base. This base can be moved in either direction, and the problem is that the mass will fall towards the Earth if it's not balanced perfectly in the center. And we have some important measurements depicted in this graph. So the first measurement is the distance r, depicting or describing the distance of the mass from the base, and then to calculate the speed or the change in position, we have two values. Either we have the angle theta or we have the speed v, and now we have taken down some of the important equations. So the first one to describe the movement of the mass is the angular velocity. The angular velocity describes the change in angle per measurement of time. And then we have the normal velocity described in the exercise, which is basically the distance traveled by the mass on the circumference of the circle. And therefore we have to calculate the part of the circumference, the mass traveled per unit time, and this is done by this formula. So basically we have first of all we have here the circumference 2p times r, and then we have to calculate how much of the circumference is traveled by the mass, and therefore we multiply it by a factor created with the angle traveled theta and the whole angle of the circle, so 360 degrees, but here denoted in as 2 pi. And if we eliminate all unnecessary terms in this equation, we basically get left with r times theta, describing the distance traveled, which is the formula described in the exercise.
Yeah. We will discuss the application of the error propagation law in measurement. Let's deliver into the important formulas on the concept. One, measurement of radius are without any error. This means that the radius values is perfectly accurate with no uncertainty in its management. Two, management of angle theta with variance sigma power of 2. In this case, the management of the angle has some uncertainty or error represented by the variance. 3. Error. This love show who uncertainties from different managements contribute to the final uncertainty. Here, f is a function dependent on variables x and y, and sigma x and sigma y are the uncertainties associated with these variables. Fear independent measurement. We assume that r and theta are independent of each other. In this scenario, the final uncertainty is calculated using partial derivatives and Funf. These derivatives help us understand how changes in each variable affect the final value. We will exercise the solutions for calculating error. The error in the calculated speed depends on the error in the underlying measurement, such as the error in the angle measurement and the radius. If the radius is measured accurately, the final error is reduced. Uh, as the distance from the pendulum's pivot point increases, the error also increases. This is because small changes in angle can result in larger larger changes at greater distances. In this exercise, we assume that error in angle measurement is non-existent. However, if distance cannot be determined with 100% accuracy, this uncertainty must theoretically be considered in error calculation. Calculation, yeah. Uh, we review the final result. The distance or significantly affect the final error. As the distance increases, the distance traveled by a given angle increases, leading to larger error. Acts The value of R acts as a lever or multiplier on the error term. This means that we need to be very precise in measuring the distance. The lower the error in the management of angle, the lower in the final error term will be. Therefore, improving the accuracy of management can lead to a reduction in overall. Thank you for staying with me so far. I hope I have been able to explain the concept of error purification and its application effectively. So,
Can we go back to the slide with the partial derivatives? Well, very interesting for anyone to use derivatives without being forced. So I'm not sure if everybody is aware of partial derivatives and why they're used. Well, apparently there's some influence by radius r and the circular speed omega. But well, does everyone remember the details of partial derivatives? I know you do. Yeah, she does. Well,
Should I explain it?
Well, if everybody knows, we don't have to explain.
Yeah, just a question. I can, for this example, give a short primer because it's pretty easy in this case.
It actually is, except for you.
The variable of the angle.
The notation.
Yeah.
It's.
The problem is
this
this graph is known and it's denoted with theta, and the task talks about omega.
In that image, I think some variables are missing. The capital L.
Yeah, I just took the most important ones for the exercise.
Maybe in principle you should have all the variables in the sketch.
Yeah.
But yeah, so everybody knows about partial derivatives. Fine, so we don't have to talk about it.
Nice.
Okay, good. I take a note of that.
Oh no. Yeah.
No, honestly, it's a very powerful scheme, and Was there any mentioning of Jacobian matrix in the book or in any of the texts?
Last section.
Yeah, so Jacobian matrix. And that was perfectly clear, so no issues with the partial loop. Perfect. This is a master course. Fine. Any other questions? No, I think Jackie fell asleep.
No, I had a similar. I had a similar concern because I wasn't sure exactly how we moved from the unicycle to the inverted pendulum. And could you show me the slide number 6?
Tries to speak. Jackie, we can hear you.
Okay, can you show me slide number 6?
Yeah.
Well, there would be another issue with the radius.
So now we can hear you.
Okay, if you could just show me slide
Yeah.
number
Sorry,
6.
my bad. Yes, presentation.
Yeah.
Just open the slide deck again. Yeah. Well,
The one before that?
take the presenting mode. Yeah.
Then the one before.
Which one? Slide 6?
Yeah, the one before that.
Yeah.
Okay, so there we have the angular velocity. Then
What happened to my explanation?
Small synchronicity.
and then the next slide. So now we have omega.
Yeah, okay. Yeah, the notation changes midway through. That's on Moss.
Okay.
Yeah.
Okay.
Yes. It's because the book uses a slightly different notation from the examples in the physics context.
Mm-hmm. Yeah, it's just a little bit confusing. That's why I had to flip forward and backwards. DVR.
So theta is basically.
So what is dv d theta then all of a sudden?
So
for the
this
partial
one
derivative.
and this one is the same. Yeah. This should be omega down here. I think that's.
Mm-hmm. Okay, and then you take the derivative of that with respect to omega, and you get r. Okay, and then dv dr. dv dr. That should be the other term.
Yeah.
But r isn't a function. R should just be a constant. R is like a.
R should just.
Yeah,
sure. This is basically the error term proposed in the book. So we took this one, and then we have down here the solution, how we applied it, and as you can see here, the term.
Yeah, He kicked me out. Oh. Were you kicked out too? Yes. Okay. Mhm.
This, by the way, holds for the presentation. So make sure you thoroughly understand.
So now we are back, and I just stopped by explaining that this one is the error term described in the book or given in the book, and then we applied it to the stated problem, and thereby the second part of this error term is left out because the distance r, so basically the distance from the base to the top of the mass, is does not have any error associated with it, so it's basically constant because it can be measured, and because of this we only get because of this the calculated speed is only influenced by the error in the measured angle, because this one has an error term and it's scaled by the distance r, which is the reason for this is because the partial derivative of the formula for the speed with respect to the angle is r, because the angle will turn to 0 and then will turn to 1, and r will be the remaining part. So the final error for the calculated velocity is r times the error of the measured angle, and then in this case squared.
Okay. Yep. So, yeah, okay.
So what does the standard deviation, what is it good for, huh?
So dv depends on theta, dv depends. So this should be omega here, okay.
Standardabweichung auf Deutsch.
And
There's some
if we look at that formula then,
and it's used in robotics. Why? What for? To annoy students?
can I just ask one more question? If we look at that formula, then intuitively I think that sort of makes sense, right? Because if you have normally distributed noise on omega, and actually it would be noise, so the mean should be 0. So then it'll look like this. Now what you're measuring is that multiplied by some constant r if this is your probability density function for your Gaussian.
Jackie, if you're doing anything, we can't see it.
Oh, you cannot see it? Oop. I draw it on the thing. Wait, I draw it on the.
Well, you need to take presenter.
No, you have to share your.
Cancel your presentation.
He has to share his camera. That's just our camera feed up there.
Yeah, okay, let me share the screen.
Yeah. Ah, yes, okay.
So, wait, how come? Okay. Intuitively, that kind of makes sense, right? We have a poorly drawn Gaussian. Not so easy to draw those with a mouse. And we have a standard deviation here. And now we multiply it by r. And then that means that all these values are going to be, this is a probability density function, PDF of our Gaussian, then we multiply it by r. So then we get that, but it'll be spread out more, right? So that's why our standard deviation is going to be multiplied by r, or our variance multiplied by r squared. Okay. What I find now, and I can follow the math, what I find interesting is that I never thought about what happens when r is less than 1. Then our noise sort of would be reduced, right?
How could a distance be less than 1?
0.9 meters.
Yeah, okay. So then you're...
And that to me seems a little bit weird. I mean, not often do we have error or variances going lower, going better for us. In robotics, usually they always get worse and worse. And yeah, so I think your math, your derivation is correct. I just never thought about it in this context. That if you and it's true, if you scale things, then your variance is going to go down. But you're not. I mean, you cannot. Obviously, you're not gaining any information or anything like that. So
yeah. So is this a problem of the magnitude of the different values?
Yeah, it's somehow related to that more than anything. Yes.
So the conversion is has to match the yeah. So the angle and the distance r somehow have to have the same magnitude.
Sort of, yeah.
So, I mean, so probably if we
it doesn't have to be. You just have to realize that you're not really gaining any information by setting.
Yeah. Sure.
Changing the.
Yeah, but because that would mean improving the measurement.
Right. Yes.
Yeah.
So I just thought that was interesting. Because until I saw this example, I hadn't thought about it like that. But other than that, your derivation is correct, of course.
Maybe you want to have another one to make sure you're using the right...
yeah, we will correct this and upload the correct presentation, sure.
Okay, any further questions? Yes, I think we have 2 more presentations, huh? Oh, apparently.
Yeah.
Okay.
Thank you.
3. Then let's rush. You have 10 minutes. We'll discuss the question in this.
Present.
So we have 2 more presentations left, yes? You?
Yeah, the group.
4. Okay. Hope you're not hungry.
It's sharing this here there? No, it's not. No, it's yes, here.
Just prepare for it, yeah? So we don't lose that much time for changing.
It's not showing us as a presentation over there. If you want to show some animation. Okay. Thank you. Thank you so much.
And maybe you can take a seat here.
Yes.
So
IT support.
Okay, okay, guten Tag. Heute Bassa und ich möchten über Implementierung automatischen Differenzierung Funktionen sprechen. Diese Implementierung ist sehr wichtig und nützlich für Maschinenlernmethoden und dazu werden wir besprechen 2 Python-Bibliotheken, die sind Nom, Pi und bei Doc. Diese Funktionen sind besonders nützlich für Maschinenlerntechniken und für Optimisierung der Funktionen. Okay. Was ist die automatische Differenzierung? Dass wir können das am Anfang dieser Mathematiker-Symbole sehen, die wir normalerweise benutzen für Ableitungen einer Funktion benutzen. Mit dieser automatischen Definition implementieren wir eine Technik, die kann uns bei Maschinenlerntechniken helfen, um die Ableitungen genug berechnen und auch wie es möglich schnell zu berechnen. Wie funktioniert diese automatische Differenzierung und arbeitet? Normalerweise die benutzt die Klittendifferenzierung, die macht die Rechnungen schnell und genug, nicht wie traditionelle Methoden. Das normalerweise haben wir in traditionellen Methoden zwei Wege, entweder numerische Methoden oder mathematische mit Symbolmethoden. Mit numerischen Methoden, das immer Ergebnisse nicht genug, die sind ungenug und benutzt Näherungen Ergebnisse, aber auch mit symbolischen Methoden gibt es Komplex und können wir nicht immer einfach rechnen. Deshalb versuchen wir, eine neue Technik zu implementieren. Mit Vergleich zwischen die drei Methoden, am Anfang gibt es analytische Methode, die benutzt die mathematische und symbole Methode und manchmal die Ergebnisse sind genau mit numerical Methoden, die verwendet numerische Näherungen für die Differenzierung und manchmal die Ergebnisse nicht genug sind, aber mit Autodifferenzierung, die AD, die ist kombiniert zwischen die beiden Methoden. Das benutzt die genaue Ergebnisse von analytischer Methode und die einfache Methode von numerischer Methode. Jetzt macht Barca weiter mit Implementierung.
Yeah. Consider this function f of x is equal to sine square of x plus cosine cube of x. We want to calculate its derivatives before we go to the Python. We will review the differentiation formula for this function. The derivatives of this function is obtained from the sum of the derivatives of each part separately. We have the derivatives of sine square of x is 2 times sine of x cosine of x. Also, we have the derivatives of cosine cube of x is minus 3 times sine of x cosine square of x. And finally, we have this formula. Now we want to get the derivatives of the function at point 1. That means x is equal 1. And we want to solve question 2 of chapter 10 and implement the differentiation function in NumPy and Torch libraries. NumPy doesn't directly support gradient calculation, but we can use libraries like Autograd that are built on top of NumPy. First of all, we define the function using deffunc. In the following, you can see the gradient function that we could use using the Autograd library. Next, we gave the value 1 to x, which must be in the form of an array. Finally, we can see the value of function at x is equal 1 is 0.8 with 8 decimal digits. In the PyTorch has an automatic calculation package, Autograd, that automatically calculates gradients. Import the torch library, then we define the function as before. Using the tensor method, we want to value x, and by setting requires grad is true, we tell x that we want to calculate its gradient. Tensor can store numerical data with different size and dimensions. Then we can easily calculate the gradient by using autograd, which we said is located directly in the torch. The result with a bit of the previous method is 0.1, which is due to different differences in methods and is natural. The output of torch, autograd grad is a tuple, and we want to say give us the first element. And Bus methods are suitable for calculating the derivatives, but NumPy is suitable for simple and quick calculation, and PyTorch suitable for complex model and deep learning. Thank you for your attention.
Okay. So next group, please get ready. Do we have any question for this on this presentation?
Everything was clear.
Yeah. So whenever you listen to these presentations, ask yourself a question. Yeah, it's, what form is it needed? Why is it needed? How does it work? What are the parameters? What are the alternatives?
Could you show me the original formula though? The function?
Screen share here. Problem is here it's showing one screen and there it's showing yours. So where's the, how can I change the duplicate?
Duplicate just two cameras, two screens. You can hide the, it's okay. If you hide it, it's okay too. Just put it into.
Let me just check here now. Stop and screen window. Can I hide here? So
Okay, here. We can try. If you
it's okay.
yeah.
Okay.
Stereo vision.
It's showing there.
Can I get an upgrade for myself?
Stereo vision.
Optical correct.
Ich habe zu Hause noch eine Stereokamera auf Pipe-Basis. Die wollte ich nochmal integrieren. Wir haben auch eine Doppel.
There's a screen there, so now I will stop here and entire screen. Why? Yeah, good. So now, yes.
Thank you. Okay. Hello, everyone. In this presentation, we would like to introduce the stereo vision. It's the simulation about applying two cameras on the same robot, so we can have and perceive the distance between the robot and the obstacle. So we want to implement it on the robot, and yeah, this is the exact practice exercise that we have to think about it and find a way through. We will ask to implement two camera on the same robot with a fixed distance. So when an obstacles or an object come to the robot, and each camera take a picture from the obstacle, and we can, and by the calculation, it will define and find the disparity. It's called, and find through some formula that we will show you. It can find the distance between the obstacles. And the thing is that you need to have a camera that any kind of camera that is VGA is okay. Then you must be the exact same pixels, or otherwise you will face errors in the calculating system. And the pictures also must be gray, because to finding the exact corners of the object, or simplifying the computation of the robot. And there is a objective of this presentation. We want to understand the concept of stereo disparity and learn how to compute the depths from the stereo disparity and demonstrate the application on the simulated area. And what is a stereo disparity? It is a thing that like we could have an experience here right now. And could you please take your hands in front of your face? You can understand how this part is. And if you close one of your eyes and see your hand, for example, left eyes, and then change it to the other side, and if you see it truly, you can see the slight shift between when you change your eyes. And this is exactly what a stereo disparity is. So this is what we are looking for, and this is we have to put the cameras on the robot at the fixed distance. As I said, it will in the formula it will be as a baseline. And the other important factor is that we need to have the value of focal length of the cameras, so we could have the disparity value, and the distance will come in a formula that I will show you further. By this is exactly what it means. if you can see in the number 1 here, it is a correlation, a reverse correlation between this party and distance. The closer the object is to you, the number of distance is very far, and when the distance is far, the number of this part is low. So, for example, if you guys at the back can see this X here with very few disparity, very few slight shift. So this is the problem. This is the number we could get relating to distance. And we will also use like this left side of this image, and the other side is right side. We can see a slight difference, very detailed slide in an angle of the camera, and we have to find a formula that can convey the size of the picture. So because we won't face any errors, because the program is like this, that will use every single pixel and with each other. So if there's only one pixel difference, you can't have the outcome that you wanted. So we will have to resize it and put it into the gray mode, and then using some OpenCV and stereo BM algorithm, which we will explain it in further. You can find out of course, and we have to have the focal length of the camera and the baseline. And this is the formula, and you can see focal length is F, and B is the distance between two cameras, which is fixed. And the delusion, that's this, and you can go.
Thank you. So in my part, I will explain how we use triangulation to determine the 3D coordinates points of the 3D coordinates points in the scene. So this is a better graphical representation for our problem, where we see the baseline here between the 2 points, between the 2 images, and the physical points there. And each point in one image correspond to a line in the other image, which is called epipolar line. And by finding the intersection of these lines, we can accurately calculate the 3D coordinates. Next, we will solve the coordinates x, y, z, starting from the perspective projection that we have, and the other variable known from the calibration, fx and fy, b and ox and oy. We will find the results for the distance. This is z, which is b, the baseline, multiplied by, as explained before, by the focal length, and divided by the disparity, which is ul minus ul. Next, I want to explain what is disparity. It is the difference in distance between the point in the left image and the right image. Next, I want to explain how will we find the point. We use the algorithm, which is called the windows-based method or the block-based method, where we take a region or a block from the image and loop through the one line to find the best match from both images to find the point. And to find the similarity, we have three metrics. One's called the minimum sum of absolute difference. The second is the squared sum of squared difference, and we have the normalized the normalized cross correlation. And let's take a look on our code. Starting first, we start by defining the focal length and the baseline. It's not shown here, but it's just a variable. Yeah. Then we load the images using OpenCV library, and then we will do the image processing. If the image is if the two images have different sizes, we will resize them. Also using the OpenCV library, and we will calculate the disparity using the pre-made method from OpenCV called StereoBM create, and then we calculate the depth using we calculate the depth multiplying it by f by the focal length, the baseline, dividing it by the disparity, and we are adding a small value so to avoid the division by zero. And then we will show the image and both the disparity visually and the depth. Next, we have our result that we got, and here we can see how the lamp here is closer and it is visible in the depth result between the two. Yeah. In conclusion, by comparing images from two cameras placed at a known distance, it's very useful for in applications such as obstacle detection, navigation, and 3D mapping to enhance the capability of robotics and in autonomous systems overall. Yeah. Thank you, and
Okay, so the next group, please get ready. But any questions for these?
Short one. The pixels, you match them only by their intensity. Is this right? Because
we have
took a black and white or a grayscale image.
Yeah.
Yeah, and then you just try to match the intensity of the pixels to find both pictures, right?
Yes, each line.
Yeah.
Okay, when it comes to robotics, of course, you can have something like map, which you do with your approach. If you would like to identify objects, maybe, well, we don't have to answer it now, but there's a different perspective to determining the distance to specific objects in robotics. How would that algorithm look?
By sending laser and getting back? You mean?
No, with your
Camera.
stereo camera. But maybe wait. Everybody just thinks about it.
Okay, thank you.
Could you show me your result pictures though? Like, where does the noise come from?
It's
Oh, Jackie.
we have a question from Jackie.
What's wrong with the audio?
Yeah, because it's connected and the microphone will be there, the speakers will be there again. Jackie, could you please repeat?
The result images, where does the noise come from in your results? Like if you look at the cupboard with the books, the bookshelf, then there on the top left, for example, there is some error. Throughout the image, there's some highlight, so it looks like it thinks something is poking out of the bookshelf. Do you know why that is happening?
Where exactly?
If you move up a little bit, yeah, there. Yes, this area, for example.
No, should be. Blurring.
My estimate.
Is this the standard image processing approach?
Blur everything.
Just take Gauss filter, increase the kernel as much as possible, go for it.
I think because it is similar patterns between the two images, we can see here that it's not that much difference between the two images. Yeah.
Okay.
I
The
think
colors
because
there's not that much difference.
but I think it's because of the white reflection here. Maybe mixed it or mistake it with the distance here. I don't know how much I'm right.
Which part?
Even if then I have no answer for it.
Okay, Jackie, go ahead. No good ideas here.
Say again, what?
There are no good ideas here, so go ahead.
Huh? No. I was just interested. It seems to me that this is quite a different, quite an interesting error mode that happened. Where could the error come from? If you have a large error like that.
I think we can make the image better using filters, and yeah, maybe we will have a better result.
Yeah, well, I think if the depth is calculated incorrectly, then there must have been a problem with the mismatching. So that would mean that your algorithm matched two parts of the image that shouldn't be matched together. And then the question is, why would that happen for this particular part of the image? So that will be just below the bookshelf, the right end corner. So then you would have to look and see where that was actually matched. If it is very far to the front, that means it would have had to move a lot more or a lot less, you know? Would the perspective distortion, the disparity, would it increase or decrease as points move away from the camera?
It will decrease if the
Yeah.
if it is more.
Louder.
It will decrease if the distance is more.
Correct. So that means it would have matched something that's far away from the actual match, right? Okay, good. Yeah, I'll leave it at that.
Thank you.
Thank you.
Ja, das heißt über Feature Codes.
Where's your presentation? How can I edit here again? Yeah.
Oh, another one.
Extend. Yeah. Why not? So let's maybe let's try like this. Yes, good.
Okay, so we are group 2 and we are presenting something about path planning with Dijkstra and A star, and it's from chapter 13, exercise 2.
Let's first we explain Dijkstra algorithm. In general idea, the Dijkstra is a algorithm is just used to find the shortest path between 2 points, and this is most likely visiting the node are likely to the part of the shortest path, and algorithm terminates when the destination node is reached. Of all reachable nodes have been explored.
Yeah, let's see with example and Dijkstra algorithm. How does it works? So the core step of Dijkstra algorithm involves maintaining set of unvisited modes and iteratively selecting the closest the unvisited nodes and the distance of the neighbors of these chosen nodes. Current distance is evaluated based on the correct distance and the edge weights, and the process continues. Sorry, the process continues. The destination node is reached. All the reachable nodes have been explored.
Yeah, so the next, the A star algorithm, some basic information. It's invented by Peter Hart, Niels Nielsen, and Bertram Ruffel. And it's also a graph search algorithm with the main part like Dijkstra, and then a greedy best first search. This is a heuristic which is added that you don't need to go through all nodes. And it also finds the shortest path between nodes in a weighted graph or in a matrix with some weights. And this use a heuristic guide to search, which we heard before. And the weights representing the cost of traveling through this graph. And the goal is to find the shortest path through.
Dijkstra's algorithm is work like it's initially define all the distance till the infinite and creating the set of unvisited node. It computes the heuristic estimates for each node, and the unvisited set will not be the empty, and selected node with it will select the node with lowest combined value, and also mark that node as a visited, and update that node as a current neighbor of the current node, and when it reach the destination, it will terminate the loops and when the unvisited set becomes or it terminates the loop when unvisited set becomes empty, or it reconstructs the shortest path by tracking back from destination node through its parent until the starting node is reached.
We solve the task 6 from chapter 13. It can read a simple map and provide a text file where one is off track and 0 indicates the free pace. And we implemented also Dijkstra algorithm to find the shortest path between the two given points and free space. Also, we implemented a star find and There's two implementation compared to complexity.
Yeah, so for implementation, we choose Python, and the map is a text file where you have 0 and 1, and 1 is an obstacle. And in the first part of this program is not shown here. We read in the map, and then we search the path. So for this, with Dijkstra, we go through the rows and the columns, and then created a queue where we have all nodes we want to visit it. And then when we have also some objects in the queue, we go to the algorithm, and when the current node we are is not the goal, we look to the neighbors and then search the nearest, go to the nearest neighbor and add the distance. And this we do so long we have some more nodes in our queue. And when at the end the current node is a goal, we return the distance and then have the shortest path.
In Estra's algorithm, we are doing almost the same, but in this we visited all the nodes, and we just visited current node and opened in the visited node. And if current node is the destination, then we will terminate the loop, and we terminate the loop, and also if not, and then look for other neighbors, and every time we append the distance, so we can get the paths by just finding the neighbors.
Let's see with understand with the example. The image showcase comparison between two algorithm, the A star and Dijkstra algorithm across the three different grid maps. Each maps contain contains a black block represent obstacle and the path finding, and the first grid in this first grid has few blocks, and the path length for same A star and Dijkstra 8, and the second in the second image has more complex compared to first one, and start with bottom left bottom to the goal, top right, and third one is also more has many black block, and finding the shortest path and the path length for same A star and Dijkstra 16. After that, both algorithms successful found the path and handle the consistency of the finding the path. Yeah.
Yeah, and task C was to compare the complexity, and the Dijkstra algorithm. In the worst case, the algorithm explores all the nodes in the graph. I think the first group today shows this, and the time complexity is O from V to plus E log V. So V is the number of verticals, so the nodes, and E the number of edges. And the space complexity is O from V, and for the priority queue also for the distance. And when you look to A star, it's generally more efficient than Dijkstra because you have this heuristic function which helps that you don't need to, in the worst case, explore all the nodes because you can pretend what's the distance when you have a good admission heuristic function. And yeah, so all in all, both algorithms have the same space complexity, but A star generally performs better than Dijkstra algorithm in terms of time complexity. For our small example, there was not such a difference, but when you have larger examples, you can see that with A star you get faster your results and don't have to explore that much nodes. Yeah, thank you.
Okay. Any questions on this? So maybe next group could get ready.
So can you, yeah, while the next group gets ready, can you just
the obstacles and the passes were always the same, would there be any configuration where the paths for A star and Dijkstra would be different?
When you have larger examples, it could be possible. But for our small example, there
Okay, how should an example look to make paths different? How much larger? Huh? Would you just need to increase the size by a factor of 2? Or do you need to do different arrangements?
you need an arrangement where the heuristic function gives some input that it's another from the Dijkstra, so that you have that the A star chooses another path.
Okay, so that would be interesting to see an example where both paths are different. But okay, so maybe we can carry on.
No, can you show your slides for the worst case time complexity?
You share your screen, right? Yeah. Do you need like this or? No, it's good. Okay. Yeah.
So, hello, we are group number 11, and today we are going to present exercise 4 from chapter 8. Here we are going to talk uh, about the smoothing algorithm that will only smoothen out the noise but maintains the edges, and what kind of filtering algorithms could we combine to achieve this goal. So first one is Gaussian blur technique. Here, this kind of image processing is widely used in the industry, but it has its disadvantages because this kind of algorithm you treats the every pixels equally. So when we are going to smooth out the images that but we want the uh, edges to be clear as much as possible, but because of the way this works, it will smooth out the whole image. As you can see in the kernel 3 by 3 and 5 by 5, as you can see in between the pixel is the size of the pixel is maximum, and when we go out the like outer side, it will decrease drastically, and because of that the clarity of edges we need, it will be like not possible, and because of that the sharpness of the whole image also will be decreased. And as you go, like if you increase the 3 by 3, 5 by 5, 9 by 9, then the image will be more blurry.
So Gaussian is most widely used technique to smoothening the image, but it has some limitation in preventing the edge. So in this case, we can consider bilateral filter. So what bilateral filter do is it will reduce the image, but it also prevents the edges. So what's the difference between Gaussian filter and bilateral filter is Gaussian filter, as we can consider, it gives the weight to the neighboring pixel by according to the distance from the center pixel. So the central pixel will have more value, and when we go far away from the central pixel, the value will get decreased. But in case of bilateral filter, it will consider the spatial distance as well as the pixel intensity. So it will consider the neighboring pixel intensity for weighting. So for example, assume that we have an edge going through and we have different pixels on the both sides of the edges. As we know, edges have difference in pixel intensity. So these pixels and these pixels have a difference in their intensity. So when we calculate the transform value for this pixel, when we apply Gaussian blurrer, the neighboring pixels will get equal weight. So these pixels and this pixel will get equal weights. So this pixel and this pixel will contribute same to calculate the transform function. So this is the reason why Gaussian filter loses the clarity in the edges. But when we apply bilateral filter, it consider the intensity difference. So this pixel will get more weight, but there is an intensity difference between this pixel and this pixel. So this pixel will get less weight. So this pixel will contribute very less to calculate the transform function. So it can prevent the edges by bilateral filter. So we take an image and we apply bilateral filter and Gaussian filter to the example image. So by using a 3x3 kernel, we can see that the Gaussian blurrer gets smoother, but edges are getting uh, losing. But in bilateral filter, it prevents the edges. So when we going to 9x9 kernel, Gaussian blurrer is getting more smoother, but the edges are not visible. But in bilateral filter, it prevents the edges properly, also reduces the noise. So that's what. Thank you for this.
Any questions? One final group, huh? Two groups. One group. Ah, okay. Ja, dann. Florian, 10 Minuten, geht das, passt das? Okay. Come on, go. Go. Next one's waiting. Oh.
Oh, das wird ein Group.
Okay.
Where's your